Hello once again, this is the Pencrest High School AP Physics 1 video series. This is video 7D, Torque Equilibrium. Okay, now, torque equilibrium is a direct application of Newton's first law for rotation. We apply this procedure to static equilibrium situations in which the object could conceivably rotate but does not. So you recall Newton's first law for linear motion, sigma F equals 0. When the forces cancel, the object doesn't accelerate. For rotation, we have sigma tau equals 0. The sum of the torques equals 0. Each of the forces acting on the object generates a torque. Those torques cancel, and the object doesn't rotate. So here's our steps. Step 1, free body diagram. Again, we know how to do that. But just to review, make sure we include all the forces at their proper locations and their proper orientations on the object. So again, where they're exerted matters now. We don't want to forget the gravitational force, mg, the weight of the object itself, oriented downward in the middle of the object. Again, all our objects are uniform and homogeneous, so their weights, their mg, their gravitational forces act as if they're exerted in the middle of the object. In C, we include unknown support forces or tension forces or whatever else is acting on the object. Now, step 2. We write vertical and horizontal force equations for equilibrium. We know how to do this already. Sigma fx equals 0, sigma fy equals 0. Again, the object is in static equilibrium, so it's not accelerating. Step 3, we pick a pivot point, also called a fulcrum. Typically, this point is going to be the location of one of the forces that we don't know. We'll see why when we write the torque equations. Initially, this pivot point will be established for you, but ultimately you may end up having to pick it for yourself. And step 4, write the torque equation for equilibrium, sigma tau equals 0. Now, elaborating on writing the torque equation, this is the new idea here, sigma tau equals 0. Each force gets its own torque term. If you recall, torque equals RF sine theta. R is how far away from the axis or the pivot point. F is the magnitude of the force, and theta is the angle between R and F. All distances, all the R's in the torque terms are measured from the pivot point. Distances are never negative. And note that the torque terms for forces at the pivot point drop out because R is 0. Once you pick a pivot point, all the R's have to be measured from that pivot point. The sign for each torque term is determined by the sign convention. Clockwise is negative, counterclockwise is positive. Again, the object is not accelerating, so we fall back on standard sign conventions. So now we'll look at a typical situation. We have two kids on a seesaw. We're going to assume that it's balanced properly and it's in equilibrium. So step 1 is our free body diagram. We have M2G, that's this kid. M2G at this end. We got M3G, that's this kid at this end. And then M1G, of course, is the weight of the seesaw itself. Put that in the middle, acting straight down. We have an Fn in the middle that's provided by the support here. So Fn is holding the whole thing up. Now we know how to do step 2. Step 2 is the force equations. We don't have any horizontal forces, so we don't need a sigma fx equals 0. But sigma fy standard sign convention. Up is positive, down is negative. So Fn minus M2G minus M1G minus M3G equals 0. Nothing new here. But now we're going to write the torque equation, so we got to pick a pivot point. Why would this be a useful pivot point? Okay, this is definitely the best place to pick for the pivot. Not only does the seesaw actually rotate around that point, but we also have two forces there, Fn and M1G, and when we write the torque equation, they will both disappear. They won't appear in the torque equation because they are at the pivot point, so their R's would be 0. So when we look at just moving left to right, we have R2, that's this distance, times M2G, that's the force, sine of 90. The seesaw is horizontal, the force is vertical. Minus R3, M3G, sine 90, that's this torque. Notice that these two go away. Now we'll take a closer look at this torque equation. This torque term is positive because this force makes the object want to rotate in a counterclockwise direction. The M3G term, this term, makes it want to rotate in a clockwise direction, so its torque is negative. Notice also that the sine 90 terms drop out because sine of 90 is 1. Now, we have another situation here. We got a man standing on a uniform beam, mass M, length L. Man's mass is 2m. He stands some distance away from the left end, 5L over 8. The beam has vertical supports at either end, A and B. So ultimately what we want to determine is the magnitude of the supporting forces at A and B. So they're going to be some in terms of M and G. So first, here's our free body diagram. We've got the mg for the beam in the middle. We've got the 2mg for the man, and that's at 5L over 8 from the left end. We've got Fa, force, supporting force at A, and Fb, a supporting force at B. Now, the beam is in linear equilibrium. It's not accelerating up or down. So again, we have Fa plus Fb. They're both up. Minus mg minus 2mg equals 0. Now we have two unknowns in that equation, so we can't solve it. So we're going to have to write the torque equation. Pick a pivot point. We'll choose point A and write the equation with that point as the reference or the pivot. Now when we look at, there are three other forces here. You'll notice that the Fa does not appear in the torque equation because, again, it's at the pivot point, so its R would be 0. All of these are vertical forces. The beam is horizontal, so the sine 90 terms all drop out. If you look at each term, R times F, again, times sine of 90, L over 2 is how far away mg is from point A. mg is the force times the sine of 90. This is a negative torque because this makes the beam want to rotate in a clockwise direction. We also have the man's mass, 2mg. He's located 5L over 8 away from point A. Times the force is 2mg and then sine 90. And then we have Fb, which is a distance L away from point A, times Fb. That's positive torque because it makes the beam want to rotate in a counterclockwise fashion. So now we clean this up a little bit. We move these two over to the other side, add them to the right side. We have mgl over 2 plus 10 mgl over 8. We're going to make a common denominator 8, add them up, and we see that the force at B is 7 mg over 4. We can put this expression back into the force equation, and that will allow us to solve for Fa, and we see that Fa plus 7 mg over 4 minus mg minus 2 mg equals 0. Rearrange it, and we see that Fa equals 5 mg over 4. So these are our final answers. We see that the man is to the right of the center of the beam, and this support therefore has to take a little more of the weight. We could, when we get to the torque equation, we could also use point B as a pivot. Our torque equation would be different. You'll see it in your notes. We would end up solving for Fa first, but the results would be the same, as you would expect. So now the last situation here, what if one of the forces is at an angle? We have a signpost here that is securely fastened at point A. It's held up by a rope that's attached at the end and is connected to point some height h above the beam. The sign itself is hanging at some distance d from the wall here. So first we need a free body diagram. We know that ropes can only pull, so when we look at the beam itself, the rope is going to pull with some angle theta up and to the left. We've got M1G, that's the beam itself, or the post itself. We've got M2G, that's the sign. And then we want to take a look at what's going on here, what's going on at the wall. The wall has to do two things. It's got to hold the post up, and it's also going to push to the right, sort of a reaction force to the X component of this tension here. So these are what we might call reaction forces at the support. Again, there's a horizontal and a vertical. The key to knowing that they're both present is that the edge of the post is fastened securely to the wall. So it's held there both vertically and horizontally. So now the first thing we need is a y direction force equation. We have Fay vertically upward. We've got 2 mg terms down, and then the y component of Ft, which is upward. So Ft sine theta. Ups are positive, downs are negative, and of course they equal 0 because the object isn't accelerating. The x direction force equation, a little bit easier. Fax is to the right, Ftx is to the left. The x component, Ft cosine theta. Again, they equal 0 because it's not accelerating. And now the torque equation. Can you see why it would make the most sense to use point A as the pivot? Okay, we have two unknowns there, and they both go away when we write the torque equation, which is really nice. So when we write this torque equation, we have Ft is some distance L away from the point A. So we have L times Ft times the sine of theta. That doesn't disappear because theta is not 90. This is positive torque because it makes the beam want to rotate counterclockwise. And then we have 2 mg terms. L over 2 m1g is the beam itself in the middle. And then we have minus d times m2g. Again, sine of 90 goes away. So there's my torque equation. When we rearrange this, Ft would be the unknown. We can solve for Ft and put it back into the force equations and get the reaction forces at point A. Okay, so that's torque equilibrium. Next, we'll start taking a look at rotational energy and angular momentum. Until then, enjoy. See you again next time.